Our research topic is planning as QBF without grounding. Classical planning problem is finding a plan from an initial state to some goal state where the state is completely known and actions are deterministic. And PDDL is one of the standard representation for these planning problems where it has two files, one is domain file and another is problem file. The domain file consists of predicates and actions, whereas problem file consists of objects, initial state description, goal state. Let's look at an example. This is a blocks world domain where the blocks world has a table and some blocks. A block can either be on another block or on the table. So there are two actions. One is unstack, another one is stack, where we can unstack a block onto the table or we can stack a block onto another block. This kind of represents the blocks world. There are three predicates: clear, if the block is on table, if the block is on another block. So this is the domain file, and in this action, for this action to occur, the preconditions must hold, and after the action occurs, the effects change the state from one state to another based on these effects. And in the problem file, we have these objects defined. Then there is this initial state. This essentially represents that B2 is on B1 and we need to reach a goal state where B1 is on B2. So we need to flip it. Okay, grounding is most of the QBF or SAT based planners use grounding as a pre-processing step where the planning problem is translated from restricted first order logic representation to a propositional problem, which is kind of easier to encode, and then they generate encodings for some plan length of k and try to find a plan. So grounding is essentially instantiating all the rules, that is predicates and actions, with all possible object combinations. For example, if we consider the predicate clear, y1 is a parameter, and we ground it with b1, b2, we get clear b1, clear b2. And the same, if we ground this action stack with two parameters, we get four different grounded actions. Okay, now let's come back to our example. As we said, the initial state is b2 is on b1, b1 is on table, b2 is clear, and we need to reach some goal state where b1 is on b2. So intuitively, we can see that we need to unstack b2, which will result in this state, and then we need to stack b1 so we can reach the goal state. So if we do these two actions, then we can reach from initial state to goal state. So this is a plan of length 2. If there are many grounded actions, it's hard to find a path from the initial state to goal state because it expands the search tree. Yes. Yeah, so there is a problem with this grounding. Given a action with m parameters, and if the number of grounded actions in untyped domain is number of objects power m, so it is exponential in number of parameters. There are some domains such as organic synthesis domains which have several parameters, which results in grounding as a bottleneck to generate these QBF or SAT based encodings. And this is one such action in the MIT exams benchmarks of these organic synthesis domains. It has 21 parameters, and then in that domain there are more than 60 objects, so the number of grounded actions are too many, so that the SAT based encodings just run out of memory, exhaust all the main memory and could not find any plans. So this is a big problem. Okay, let's look at a little bit more deeply into the organic synthesis domains. So organic synthesis domain, so the domain file consists of set of reactions where the problem file consists of some initial molecules, so which is the initial state, and then we need to reach some target molecule, which is the goal. So here, if you look on the left, this is one of the examination questions in MIT organic chemistry. So there are these benchmarks which are encoded into PDDL. So these questions are essentially encoded into PDDL, and then we can use the planners to solve these questions. These domains received an outstanding domain submission award in IPC competitions 2018, and they are quite hard to ground. Okay, so now in the next of the talk, so we first look at a simple SAT encoding, and then we get some observations from the SAT encoding and try to figure out how to avoid this grounding by using the structure of the constraints that we generate for these propositions. And then we look into the QBF encoding. Then finally we discuss the results for these organic synthesis domain benchmarks. Okay, planning as reachability is a wide known topic. So essentially a planning problem corresponds to a reachability problem, where finding a plan corresponds to finding a path from initial state to goal state in some corresponding graph, where each node is an assignment to the propositions and the edges are essentially the grounded actions. So if there are n propositions, the propositions we get by grounding the predicates, the total search space is 2 power n. There has been significant research in SAT-based planning. Kotz and Selman proposed the initial SAT encodings and improved by Rintanen, which allow the parallel plans, which is the current state of the art. There are other improvements such as action splitting, explanatory frame axioms and invariants, but all these based on the grounding as a pre-processing step. So the bottleneck still holds. Okay, let's go back to our example. This is the initial state where B2 is on B1. Then we apply the action unstack B2 B1. This particular state in time step I occurs. Now the corresponding representation using the propositions looks something like this. So here we have all the propositions. Green means it is positive, red means it is negative. So we say B2 is on B1 is true, B2 is clear, and B1 is on table. Rest of them are false. And after we apply this action, we result in B1 is also clear, B2 is clear, B1 is on table, B2 is also on table. Rest of them are set to false. Now, if you look at the definition of this action, we have preconditions. B2 must be clear, which is true. B2 must be on B1, yes, that also holds. And because of the preconditions holds, we can apply this action. Now in the effects, we say B2 must not be on B1, we set it to false. B2 must be on table, we set it to true. B1 must be clear, we set it to true. And every other proposition which is not touched is propagated. So we have three kinds of clauses here. One for preconditions, another for effects, and other one for propositions which are not touched. Based on this, we generate a SAT encoding. So here is the structure of the SAT encoding, where this essentially says there exists a plan which is a sequence of actions. So these are the action variables, parameter variables, which are binary representation of a grounded action for each time step. And there exists a sequence of states such that the initial state holds, goal state holds, and the transition function holds between two consecutive states. So F here is for each proposition we define a corresponding variable for each time step to represent the state. Okay, now the transition function is the interesting part, where we get where we need to handle the exponential grounded actions. So transition function is simply a conjunction of all the clauses for each proposition, and for each propositions we have three types of clauses: for preconditions, for effects, for frame axioms. As we discussed before, for each proposition, if the proposition is a positive precondition for the chosen action, then we set it to true in time step I, or we set it to false if it is negative precondition. In the same way, we set the proposition corresponding variable of this proposition to positive in I+1 time step if it occurs in the positive effects of the chosen action in the plan, or negative if it is a negative effect. So if it is none, so if the proposition is not touched, then the value must be same in the both time steps. So this kind of summarizes the clauses for each proposition. Let's look at an example. So the ontable B1 is a proposition, and ontable B1 is set to true in time step I if either the stack B1 B1 or stack B1 B2 is set to true, because these actions contain this ontable B1 as a positive preconditions. So if the plan has this particular action, that means this must be set to true in the time step I. And the same for the effects, and here the frame axioms. Yes. Okay. Now, as we can see, the values of the propositions only depend on the actions. They don't depend. They are independent of each other. That means we can enforce these constraints like in the time step I and I plus 1 independently. In other words, given an initial state and a sequence of actions, the consequent states are known and fixed. So we can enforce the constraints on the proposition separately. So that is a key observation here. Okay. Now how can we use this observation to generate this QBF based encodings? So because the PDDL description is already gives the constraints on the predicates directly, and then there is this grounding step where we generate propositions. We avoid that by representing the parameters as the universal variables. So it represents all possible parameters, and then we generate the encodings for each predicate directly. So that is a key idea. Okay, so here we have the QBF encoding. So the action variables are the same as Saturn encoding. Instead of the proposition variables, we have a quantifier alternation. We say for all object combinations, there exists a set of predicates for each time step. So this for all object combination and there exists predicates represents the propositions when expanded. We say initial state holds, goal state holds, and the transition function holds. Quite similar to the Saturn encoding. Okay, here the interesting part is still the transition function. Instead of we say we don't generate clauses for each proposition, here we generate clauses for each predicate. Now for each predicate, if the chosen action has the predicate as a positive precondition, we set it to true in time step I, false if it is a negative precondition. And the same holds for the effects too. Essentially the difference is that we generate clauses for each predicate, and then we represent this action clause, which is a condition, which is an ungrounded state. We'll look at it in a bit. And then there is this frame axioms. Okay, so the ungrounded action, so this represents how do we define the ungrounded action clause, which kind of forces the corresponding predicates to either true or false. We look at the example to get a little bit better idea. So we consider the ontable is a predicate. In the Saturn encoding we looked at ontable B1. Here we consider ontable. So here we say ontable is set to true in time step I if the chosen action is stack and the first parameter is equal to the for all object combination variables. So in that branch where the object combination variable is equal to the first parameter, then we force it to true, kind of enforce. And we have positive effects, negative effects. Essentially these values are forced in the specific branches of this for all variables. That's how we can ensure the correctness. And when expanded, these clauses will be equivalent to the clauses in the Saturn encoding. Yeah. Okay, so our planner, Q Planner, which is an open source, is available online. So it generates ungrounded encodings when given a PDDL specification of a problem for some k. So the Q Planner calls external tools such as Cake Solver, which is a QBF solver, and Blocker, which is a preprocessor, It is modular, so that means we can call different QBF solvers and different preprocessors. So for the comparison, we consider 4 organic synthesis benchmarks. We allow 300 GB memory and 3 hours time limit. We generally don't use 300 GB for QBF, we just use less than 20 GB. But we allow it for the case of SAT based. We have an extended version of the paper where we also consider 20 other IPC domains and we compare with the simple Saturn encodings. Now coming to the results, Madagascar is the SAT based state-of-the-art planner. It could solve only one of these instances and it uses 117 GB. And in the rest of the cases, because of the grounding, it couldn't solve it. Whereas our planner, we could solve 57 of them altogether and 28 of them uniquely. We also compare with FTS, which is a non-SAT based planner, which is the winner of 2018 IPC competitions. It could solve 31 instances. There are 2 instances where it solves uniquely, so it's kind of orthogonal in some cases, the non-SAT based approaches. Yes. Our planner usually takes less time other than 1 or 2 instances compared to the FTS, and we use significantly less memory. And when we consider the other IPC domains where grounding is not a problem, which is an extended version of the paper, the SAT based and non-SAT based planners outperform our approach. We perform quite well when there is a grounding problem, and the others perform well when there is no grounding problem. Yes. And in the consider the future work, we can generate even compact encodings by considering these iterative squaring. That means we avoid the unrolling of the transition function, which we do right now. So that can be avoided. And we could also experiment with different QBF solvers or preprocessors, or we can consider the harder problems such as conformant planning. But the main idea here is that we consider this universal variables, universal quantification to avoid the grounding and represent these encodings directly from the restricted first order logic descriptions. That way we are able to generate these compact encodings and circumvent this grounding problem. This can be used in other reachability problems such as bounded model checking, and there are many other domains where it can be useful. Yes, thank you.